Okay, so let's continue with this where we want to have the complete design where all both the data path and the controller uh, is connected together so that we have something like this. Yeah. Okay, so we will have both of our design just now, which is the CU and the DU data path, and this we call it DU. No, this is CU, and this is data path unit, and we have the output from this is the control signal, and we have 6 signal, right? And the DU we have input, which is data in, and we have output, which is data out, right? And actually we have the extra, yeah, this is for simulation. The name is rec1, rec2, rec3, right? And of course we have the clock also, and the reset into this. Okay, and this signal is named LD1, this is LD2, this is LD3, this is SEL1, this is SEL bit number 1, SEL bit number 0. Okay, and of course we have the clock as well, but this is negative age triggered. The same clock signal as with this one, but this one is positive, this one is negative age. And we also have the same reset signal to this. And we have another output, which is state actually from here to see the present state in the simulation, right? So we want to create this circuit, right, in Verilog, but we already have this design, and this design we just connect this together, right, to get the complete one. So we can create a new one, new project, right? Next, the name here is let's have a new folder. We call it CU DU 5, maybe CU DU enough. Right, the name is CU DU. Next, now we need to have the previous design attached to this add file, so we can attach this CU into this also, because we want to use in our design here, and also the DU add. Okay, and we can finish here, and we create a new code Verilog, and the name is this, and the list is should be based on this. Yeah, we have clock, reset, state, this and this and this, right? So we should have clock, reset, state, the this data in, we have data out, we have rec 1, rec 2, rec 3. Anything else? No, right? Our input, the 1-bit input should be this, right? And also we have 4-bit input, which is data in, this one, data in. We have output, all right, the 4-bit, which is data out. Also rec 1, rec 2, and rec 3. And we have another one output, which is the state here, which is 2-bit. Okay, so we have this, everything here, and now here this should be declared as wire in this case, right? LD1, LD2, LD3, SEL1, all are 1-bit, and we have the 2-bit. SEL2, right? That's it. Now we can instantiate the CU into this. All right, so our CU name is maybe we can have here, open this CU. All right, so the name is this. So just use this name. This case is here, name, and let's name this module as CU. Right, the control unit CU, this one. And the port list should be the same as this one, the arrangement, and the signal name is the same here. We use the same name, so we can just copy here, and that's it. And we also need the DU, so we can have the DU, this one. This is the name that we want, and let's name it as DU, just like this. And also the name for this, we use the same name, so we can just copy all of these to this. All right, so we have all of this already, and any other signal that we missed? No, so just add module. All right, so you see, if we have the sub module already, so to create this is easy, right? Using a hierarchical design methodology, and we use the structural modeling here, right? So it's quite straightforward, and we just save this one, save, and we need to save inside here, save, and try to synthesize and see what is wow, we have 11 warning, and again we need to check, and it's actually, this means that the previous warning, yeah, in this yeah. So if we change to this to 00, we should have no problem, right? so we should have no problem. So this is actually from this the three-state buffer that we create. So in our case, should be no problem as well, actually. Right? So this warning can be ignored. Okay, so we have the design already. Now we need to create the uh, touch band, right, to simulate our design. Again, we need to create a new Verilog file. Attachment, you need to have time scale. In this case, we use 1 nanosecond time unit and 1 nanosecond precision. And for module name is, let's name it the CU DU dashband. All right, and we have the input to the dashband and the output to the dashband. We can use the same name here, is input and output, right? So and remember, this must be rack in dashband, and this should be declared as wire. This also should be declared as wire in dashband, right? And we instantiate our this design. The name is this, right? DUCU, and let's name our dashband as design under test DUT, and the port list, as we use the same uh, port name here, then we can just use the same here, right? Now we can have uh, the setting where we want to monitor this the time unit, and we want to monitor all this data actually in this signal actually. So we can just copy and paste, and okay. And it should be in the form of binary, and we should finish here. And of course we will map to this, right? Is it everything? Yes. Okay, maybe we here we have our clock signal is starting at 0, and we create our clock signal using always, and the it's changed. We change the clock or toggle the clock at every 10 nanosecond. All right, means that our period is now 20 nanosecond. Okay, and now we have the stimulus, the input vector to our design. So at time 0, what we want to have. Okay, so to have this, maybe we can do something like this. Okay. So we have the clock signal. So we want to create the signal like this. This is our clock. All right. So we can have our, and this is our reset. Okay, so this is 20 nanosecond, this is 40, this is 60, 80, 100, 120, 140, and so on. And maybe we have a reset signal from 0 to 25, and after that we let the reset to be 0 all the time. All right, so we reset here, reset first, and then when we start here after reset, so this should be state as 0, and again our remember our finite state machine is negative age triggered, yeah. So S0 should start here, right? So this should be S0, and the next one should be S1, and this here should be S2, and back to S0 again at 100 nanosecond. So here, if this is S0, so maybe here we have data in. We set start here the data in after reset, maybe we make the data available here. All right. Okay. So this is data 1. Maybe we have number 5. We put number 5 here, right? Until what time? Just before another one. Maybe here is 25 until somewhere here. We change the data, to number 6. $30 plus $50, $80, too short. Right, maybe until this. Okay, and then we change it to the new data to number 6. All right, so that here we read a new value which is 6, and let's see what is inside rack 1, rack 2, and rack 3 should be according to our specification, right? So we want to create this. Okay, so at 0, we make sure that the reset signal is equal to 1. All right, and we have no data in yet. Maybe we put it 0, and after 25 nanosecond, we make reset equal to 0, and data in we have number 5 here, number 5, and let's, for example, another here is about 50 or 60 nanosecond, 50 nanosecond. We have a new data in. This is number 6, and let's run this simulation until another 100 nanosecond. And we stop the simulation, and here, and module, right? So now let's see what happened, and try to start. So we need to save this, and the name should be this, yeah, and we save. Okay, and try to run here. Oh, we have error. Okay, so what is that? Oh, y input should be initial, right? Initial. So it's a syntax error. Okay, so just the previous warning, then we know exactly what is that warning, so it should be no problem. So we have done that, and let's look at the simulation. So we need to have a simple setting here, and we use model sim Altera, and the output format for netlist is Verilog, and we compile the test bench. So the test bench name is this, and the file is this one, and should be okay. Okay, and now we do the RTL simulation and wait for model sim to simulate. All right, start running now. Okay, so I have my waveform here. Expand this and make it full. All right, so this is in binary, so I want to change to unsigned so that I can see exactly. All right, so here, this is our data. This is our data exactly based on what we write in our test bed. We have data in equal to 5 here at 25 nanosecond, and here we see that our state, yeah, this is state. So we can see the state here because in our design here, we have this. We have this state as our output, right? And in our CU, right, we have this. That's why we can see the state in our simulation. So this is state 0, is actually start here, and this is reset. Actually, it's always 0. State 0 is start here because it's our final state machine is a negative age trigger. So this is state 0, and we can see that if when state 0, this data out should be, yeah, we can see that at the positive edge of the clock here, this is positive edge, the data is transferred into rack 1, all right, in state S0, all right, here, okay, and we see that as rack 2 is still 0, rack 3 is still 0 because we reset, yeah, we do the reset before that, so there is no data, should be 0. So there is no data yet, but in art rack 1 we have number 5 already, and next clock cycle here, state 1 S1, this is S1. S1 we move the data from rack 1 into rack 2, this is rack 2, we have number 5. So the data is moved from here to here, number 5, in state S1, all right, and in state S2, the next state, we move number 5 from rack 2 to rack 3. Yeah. Okay. And we see that this is why we use negative age triggered for state, yeah? Because we want to have the data transition, make sure that the transition is in middle of the state. That means that the state is stable already. We can see that before we transfer the data from here to here, from R1 to R2, we can see that this happened when the state is stable at the middle of the state, yeah? Not at the same time as the state transition. This is not good because sometimes if this is faster than your state diagram, so you may have an invalid result here. All right, so we make sure that this one is, yeah, half clock cycle slower than the state transition. We make sure that the state is stable first before we move the data at the positive age clock here. You see, this is exactly in the middle. All right, so we make sure that this is, yes, in state S1, right, same as this one. In the middle of state S2, we move data from rack 2 to rack 3, and this is the new cycle. Yeah, this is state S0. We have a new data here, number 6, and we can see that number 6 is transferred at state S0, transferred to our rack 1, and the next S1 is transferred to rack 2 already, and the next state S2 is transferred to S2 here. All right, so this show that our simulation is correct, and of course our design is correct based on this simulation. So we can have another data to see if you want to look at more data. All right, so this is our simulation based on our design. All right. Any question for this? Okay. So if no question, we back to this. So we have the design also, and you have the code here, or maybe I will share the new code for the what we have done just now, because the code is maybe a little bit different from this. All right, but it's actually uh, uh, produce the same result. This one is a little bit. This is wrong. This is 4-bit actually, 4-bit, and this is not rec 1. Change this to okay. This is mistake in the notes. So in the notes, there is a little bit mistake here. Wait, look at the note. Um, all right. This should be no problem. But here we have actually this is not red one. This is oh yeah, this is correct. Red one. This is red 2, and this should be red 3, right? 10, and this is 4-bit actually, and you have that. Okay, other than that should be okay. Right, so this is the code, and this is the CU, same CU, and this is the connection, the integration, and CU. All right, a little bit different, but you can have a look at this. Same things, actually. And this is another example, right? Using number 9, you can see that 9 is transferred to R1, R2, R3. 1 is transferred, right? E transferred in, right, any data. Okay, so I think we are at 11:30, and this is what we will look after this. Maybe we continue next week. Yeah, another half of this chapter for next week. All right, and we will finish this chapter next week. Right before we go to the next one. We have another example here. All right, you can have a look at this, and we will do some exercise here before we go to the final chapter of this course. Okay, so I think today we will end the session here. So if you have any question, you can always ask. You can ask now, or maybe you can ask through the WhatsApp.